Okay, Assalamualaikum warahmatullahi wabarakatuh. Today I would like to present my research progress. The research titles is Design and Implementation of Model Identification Adaptive Controller for Closed Loop Control of Knee Extension using Functional Electrical Stimulation. My name is Haru Aruf. I'm a master student. My supervisor is Dr. Emilia Nusal, and my co-supervisor is Dr. Saiful Zaimi Yahya. My student ID is 2019153743. Okay. I would like to start with spinal cord injury, which is called SCI. The spinal cord injury can cause loss of function for limb to make movement. This is because of the brain electrical signal for making such movement has already obstructed to reach muscle motor unit. This is somehow is the effect and the symptom of stroke and also spasticity. The rehabilitation process indeed used to recover the functioning of the limb, and it can be done in a traditional way, which is also called a passive way, through massage and exercise. For the active rehabilitation process, it involves a device which is called functional electrical stimulation, which is FESS. The FESS use short electrical pulses generates and being passed to the muscle through skin via electrodes, in which this causes the muscle to contract and the movement is made. And slowly it makes recover to the motor nerve and sensory nerves. The op the FAST device is controlled through open loop control system, and also the open loop and the closed loop control system. The open loop FAST system require continuous trial and error from user uh, to give input that's finally to input to the device to charge the device to the muscle, um, and this could results in early muscle fatigue phenomena because it is done by trial and error. But in the closed loop feedback fast controllers is expected to give a better performance because it can change the amount of charge being applied and transferred to the muscle. But indeed, in the real world, the closed loop fast controller is observed working under performance. This is most of the time due to the non-lattice effects such as fatigue, spasticity, and spark. Rehabilitation through knee extension. This is considered an early exercise or early stage of rehabilitation before it can be proceeded to the others, which is more advanced, such as for knee swing, cycling, rowing, standing, and finally walking. At this stage, the muscle is still sensitive to electrical charge variations, and careful measures need to be taken to avoid overstimulation that can cause further injuries. The muscle need to be extended as much as possible to maximize and to allow the muscle to contract as further as it can. And also we intend to have the time for the muscle be extended to be maximized. Problem statement. The non-nullities of fatigue, time delay, overstimulation, stiffness, spasm, and spasticity not only cause degrade in muscle force, which cause end of the rehabilitation exercise, but also prevent closed loop controller to be tuned to the system under control. This leaves option for tuning the controller be done at the simulation model. As the result of tuning at the simulation model, the conventional closed loop controller may work under performance and almost work under performance as it's not tuned to the actual systems under control instead of using simulation model. That lack of accuracy and the non-nullities which is unknown as not added to the model. The conventional closed-loop feedback controller are unable to detect non-nullities owned by the patient or resulting from the rehabilitation process itself or changes of patient under treatment because different patient has different non-nullities effect. So proper adjustment could be made to the controller. The conventional closed-loop feedback controller also is not optimized, tested to the system with non-nullities effects at the stage of development, which causes it perform bad performance and sometimes failure during the real phase rehabilitation as is facing system with non-nullities. The robustness and the flexibility of conventional closed-loop feedback controller is not tested to control at several reference points or in the presence of disturbance to confirm its robustness ability. The conventional closed-loop feedback controller has no features and mechanism to adapt to such non-nullities effects, making changes in the closed-loop feedback controller settings to adapt to the changes and to maximize the closed-loop controller performance. Research objective. To design and develop a new model, and this is such a model that has non-nullities effects, and the model is established in a physical-based models and also in the numerical methods for closed-loop feedback controller tuning and optimization. The physical-based model and numerical will be established using MATLAB Simulink software. Development of system identification method to detect non-nullities and system changes as a result of degraded muscles and changes of patient under treatment. Objective number 2. Objective number 3, to optimize the closed-loop controller by tuning using particle swamp optimization to system with non-nullities for several reference points and possibility to increase its robustness. Objective number 4, development of adaptive tunable closed-loop feedback controller with control law formulation and lookup table, which allow changes on patient be detected and a rectification to the system can be observed. Research gap. The successful of the rehabilitation exercise depending on the patient voluntary during the exercise, proper control of rehabilitation assistant device such as FAST, and a maximum time for the rehabilitation exercise be conducted. It is found that it is found in the literature, there's a very few covers control with the coexistence of non-nullities such as fatigue and time delay, stiffness and spasticity. It is found in the literature that Very few covers control with consistent of nullities, such as fatigue, time delay, stiffness, and spasticity, while the nullity itself are always associated and indicate the actual situation of patient who require rehabilitation. And the focus are still on the closed loop control performing, leaving the optimization, prolonging, maximizing the rehabilitation time as the crucial matter. The final result and finding of the total time taken or the extension of the total time of the rehabilitation are rarely available in the literature. The robustness test when dealing with disturbance and testing to control at different reference points are rarely being found in the literature as well. In the freezers, the main focus of the adaptive controller is to control the system under non-linearities while still optimizing the closed loop control performance and to maximize or prolong the rehabilitation time. Scope and limitation of study. The scope and focus of this research works are limited to lower limb rehabilitation exercise, specifically knee extension, using MATLAB Simulink software. Detail of the scope for the research works are as follows. Develop knee extension model contain analyses of stiffness, fatigue, time delay, and spasticity only. The developed system dimension controller and formulation are specially for fast-assisted knee extension rehabilitation exercise. The design tunable adaptive feedback controller is meant for sliding mode control for closed loop fast controller by gate setting changes and optimize using particle swap optimization. The system maximum effect is set to 3 Newton meter from 0 to 35 degrees. The span spasticity range from plus minus 4 Newton meter. The time delay is maximum at 0.26 seconds, and the fatigue effect with 3 stages at 0. Newton meter for the first 4 seconds, 0.4 Newton meter for the second, and 1 Newton meter at the remaining. The knee extension simulation model developed using physical-based model, and for the fast model using MATLAB Simulink drag and drop icon. The numerical computation method for the knee extension simulation model is developed using Taylor series and Laplace derivatives. Some literature on the feedback controller. PID is the most simple and easy to be implemented in real world, but the performance is slow to control the process that has non-linearity effect. PID can amplify high-frequency system dynamics and lead to system instability. Neural networks is the most complicated to be implemented in the hardware environment, but it does not require a mathematical model, and the performance is much better than PID controller. Several input signals can be fed to neural network, while this provides more information for better controlling. But neural networks suffer stability issue and too slow for online optimization and need to be trained offline. Sliding mode is a non-linear controller, but it suffers the effect of shattering, and it requires a mathematical model to design the sliding surface. Fuzzy logic is easy to be implemented, real-world implementable, tunable online, does not require a mathematical model, less shattering, and the performance is much better than PID controller, but it has lower control bandwidth. The use of an equation-based controller such as PID may offer this flexibility but may not be sufficient to adapt with the dynamic characteristics of the muscle. An intelligent controller such as fuzzy logic is the popular and have better capability of adapting with the dynamic characteristics of the muscle, while modern controllers as sliding mode is known for robustness. Adaptive type of controller are currently active, replacing the conventional controller, with advantages of handling disturbance, uncertainty, and mismatch model. Although several of feedback controllers that have been employed in the FAST system for knee extension, Sherrod et al. Concluded that all those feedback controllers were still not ready for real-world FAST application. Jeselnik et al. Also did the same comment referring to classical control. From the previous study, it was found that the feedback controller has several discrepancies when minority of muscle, fatigue, spasm, and spasticity effect, which are listed as follows. Inaccurate modeling, no mechanism to handle seasonality, no adaptive tuning are the cause of problem to the conventional closed-loop feedback controllers. The controllers are tuned during simulation stage due to master degraded performance, and it doesn't allow for online real-time tuning. At this tuning state, fatigue and other disturbance either are not included or lumped into one expected value to represent it. This has resulted in an inaccurate model for tuning. The most difficulty faced by the feedback controller is oscillation and stability issue as a result of stiffness, sparsity, and the time delay effect. But there are no mechanism on handling this issue which cause drop in controller performance. The controller should be retuned according to the current patient status, but this retuning feature is not available or present in the conventional controllers. This results in poor controller performance due to inaccurate tune setting. Due to this problem, present researchers are working with adaptive type controller. While the adaptive type can handle problems related to effect of uncertainty, disturbance, and mismatch model, but it can improve and handle certain part of narratives. The recovering effect also not last long as the narrative, fatigue, time delay, stiffness, sparsity degrade increases. So the system and design overview that I propose is a model identification adaptive controller. Model adaptive controller, MIAC, as in figure below, is one type of adaptive controller where it can perform system identification while the system is in running. So you have system identification, adjustment mechanism to the controller and controller plan. So this is the simpler block diagram. So this that is study mock feedback controller. It has dynamic mechanism. You have lookup table in which there is a main control unit for system identification, and also for the controller to find the controller settings and be passed to the tunable feedback controller and to control the system. Operation in a feedback adaptive controller. The adaptive feedback controller has features acceleration, ovation, the output response. The feature acceleration, it extracts parameter which is later used to access a lookup table to find the best settings through formulation, controller, and lookup table. It has interchange controller between sliding mode conventional and unshunted and direct control or feed-forward control for feed-forward assistant in dealing with nonarities. So when there's nonarities, so the controller can change between using the conventional sliding mode to the more advanced, which is unshunted sliding modes, and sometimes it can operate the direct control and feed-forward assistant when dealing with certain nonarities. The control load closed loop controller, which is sliding mode, gain setting from lookup table. The closed loop controller will control the system, while at the same time it observes the fatigue and overstimulation and will do necessary action when this fatigue and overstimulation is detected. Research methodology. First, we establish the simulation model using Velting linear differential equation, and then we incorporate that with the fatigues, time delay, elasticity, spasm, and sparsity, which we get from this Ferrarin and Pedotti, and also from the Cheryl. So we combine it. Then with all this, we form the physical-based model using MATLAB Simulink. This simulation model, the physical-based model, offers several advantages such as faster and can be linked with the external device or controllers such as FPGA or microcontroller in the case we want to test the controller using the processor in the loop technique or hardware in the loop technique. From the physical model that already established. We then convert it to numerical computation using Taylor series or a Laplace derivative. Because when we convert it to this numerical computation, the simulation time, the processing time will be faster, which is very much suitable when we intend to tune the closed loop controller using particle swarm optimization. While we simulate with physical based model using MATLAB Simulink, it might take 24 minutes, for example, but when we simulate the same thing using the numerical method, it only takes 2 minutes. So it will be much faster. Then we establish the system identification techniques via feature extraction using digital signal processing. This is used to detect, to obtain the time response of the system, the overshoot, the steady state gain, and to detect stiffness, to detect spasticity, detect time delay, and also fatigues. The system as the identification has to function. Number one, during the PSO tuning. PSO tuning, we use also digital signal processing for performance evaluation. For example, we want to know the rise time, the overshoot, the settling time, the steady state error, and if there is oscillation during the tuning of the controller using PSO. And the second time, when we use this system addition via feature extraction to detect the stiffness, the spasticity, the time delay, the fatigue, as well as the time response, overshoot, and steady state. Then we use expert system or algorithm of tunable closed loop controller, which allow adaptive sliding controller setting be changed according to the patient. This expert system performs this control law, which is depend on condition of nonlinearities and the system performance. We use this control law, which is based on expert system to obtain the control setting, which is stored at lookup table. Objective number 4, design and development of closed loop feedback controller optimization using expert system and PSO to optimize the closed loop controller performance. And then design the development of direct control method and shutter sliding modes to improve the closed loop feedback controller. And then on completion, we establish the lookup table. The data collection, data analysis testing, or data analysis, data testing for procedure and its control be done using MATLAB simulation model software. Some of the results, this is some of the results, which is represent the system performance and the action that will be done by the controller. For example, in this case, the muscle is low, the muscle torque is low, so we do exercise at much lower reference angle. And this one is for the time delay. We see the oscillation effect. So we change it to these unshuttered sliding modes, so it can operate when we apply direct control to improve the performance. And this one, when we and then the system identification detect fatigue. So we change the control reference, so we can prolong the rehabilitation time. And this for stiffness, we detect stiffness when we change the control testing. So we try to avoid oscillation that later will cause a stability issue to the control performance. The same thing with the spasticity. And we detect spasticity, so we do some changes on the control setting to allow it to perform much better. And this one, when we detect disturbance, we also can do some changes on the control setting by find the right control setting at the lookup table. The research contribution. The research contribution consists of development of physical-based model of knee extension, development of numerical method computation using Taylor series, development of feature extraction and system identification to detect fatigue, stiffness, spasm, sensitivity, time delay, and also the performance. Development and formulation of control law and lookup table, development of tunable closed-loop feedback controller, development of technique of assistant of technique such as direct control and feed forward. So the expected of the identical control system under non-reduce fatigue, stiffness, sparsity, and time delay. Can change control reference when fatigue of simulation detected. Change control reference according to the patient condition when low muscle power detected. Detect fatigue and overstimulation and prevent muscle injuries and prolong the rehabilitation exercise. Completion status. At this moment, 4 papers have been published, 2 Q2 journal and 2 book chapters, corpus, and 1 paper is still under review. There are several papers also is under writings. Completion status for thesis is at more than 70%. Overall conclusions, the overall research work is 97%. Things to do is writing thesis correction, and also paper correction. At the same time, I still working to draft papers and to arrange the result, some of results from a few papers, direct control, arrange a result for the thesis as well, for paper, and also for this thesis. Say a few papers. Arrange result. Some of the result that will be placed in the thesis, which coming from the paper that's currently under draft. Okay, that's all, and thank you.